Okay. Let's start then. You can see the slides, right?
Yes, ma'am.
Okay. So far, whatever we have discussed, like how we are doing the modeling, and then when we are starting to write the software or we are analyzing the software, we have talked about how the pipelining strategy or how the memory organization, they are affecting the overall design, or especially the performance of the design. So what we know that whenever we have chosen one backend, we know what is the pipelining strategy given for that platform, for that process. Also, we know what is the memory organization for that processor, what is the cache handling timing, required timing, cache to man, communication timing, data fetch timing, etc. So all these things, and also what we have seen that another timing requirement can come from secondary memory to main memory transfer. But frankly speaking, when we are going to this embedded domain, the usage of this type of secondary memory is not very prominent. So you will see whenever we will discuss now, or whenever we will you will do actually with Professor Shorter probably, that WCT analysis, execution time, worst case execution time analysis, those parts, we will always think what is the effect of this cache and main memory communication effect in our performance. Not much about the secondary memory. So these parts are, what I mean to say, these parts are very deterministic. When I have chosen already one backend, the rest of the things we know. But this third part, interrupt, that we are going to discuss today, this is, we can think, the most non-deterministic part of our performance timing analysis. Why? Because what we know, what is an interrupt? That interrupt is a mechanism that is pausing your ongoing execution. So whenever you are facing an interrupt, you have to stop your ongoing execution. You have to load some predefined interrupt service routine and execute whatever code sequences you have written within that. Okay. So the way your interrupt handler is handling the interrupt, any interrupt, that is also very defined. You have already written some code, some routine is there. But what is not defined, that when your any interrupt will actually seek for the attention of your system, so that you have to stop your ongoing work, your routine work, and you have to attend that interrupt. So that part is non-deterministic, but that part plays a very critical role when you have to do that timing analysis. Now, these parts, I think most of you know that there are three types of interrupts mostly we handle. One is hardware interrupt, when the interrupt is coming from any external hardware. Software interrupt generated by some, as in maybe as some software instruction, and exception, that is a trap that is coming from your hardware, internal hardware. So mainly hardware, when we are telling hardware interrupt, by that we mean that the interrupt is coming from any external hardware. So interesting part is that whenever any interrupt comes or interrupt occurs, so what you have to do, you have to store whatever ongoing process was there. That status you have to store in this PSW. We can, that basically means program status what. So you have to store the status till which point you have executed, and related other register details, everything you have to save, and also the return address, that whenever you know that after that you will be handling the interrupt, you will be entering in the interrupt handler code part, And next, you have to again come back to this main program. So from where we will start. So that return address, the program status, what. So all these things you have to store. And then you have to basically execute whatever instructions you have written inside your interrupt service routine. Now, though this part is deterministic, but when that interrupt will occur, that leads to some amount of non-determinism. So that's why whenever we are modeling, we will see how we can model that and how we can code that in our overall coding. But these parts lead to non-determinism, and we will see. I mean, maybe next week we will start discussing a few words about our embedded communication networks, few communication protocols. There we see whenever we have these type of event-driven instruction request occurs. This interrupt, you can think of an external event has occurred, and that event is basically requesting your system to process something different than your routine work. So this type of scenario is very common when you are thinking about your embedded system design. And that's why whenever we will be talking that embedded communication protocols, there we'll see some special features we need to add to handle these type of extra event-driven situations that are so that the communication should be separated in such a way that if your routine work is also real time, that is something you have to complete it within a fixed deadline, this type of interrupt may not disturb, should not disturb that real-time requirement. That means the challenge here is something is coming to your system, some instructions, these set of instructions you have to execute the course of your execution. Whenever this interrupt request will occur, you don't know when the request will come. So whenever you are doing, because real-time analysis when you will be doing, that is the main requirement of your embedded system design, that you have to predict that within this time, this is my deadline, and I can complete my task within such and such time or such and such time and deadline. But when some unpredictability comes and that adds some extra instructions, then you have to support some extra time, extra resource for those instructions. So handling this part itself is a challenging task when we are talking about embedded software or embedded system design. Okay. Anyway, this is the way that whenever interrupt occurs, you are jumping to this interrupt service routine, and when you are finishing this interrupt service routine, this whole part, you are again restoring your previous ongoing program from this program status code, and you are executing from the next instruction. See, you have stopped here, stalled here up to instruction +2, and then you are starting from instruction +3, this part. So this is the way, this is the soft code, how we can realize the interrupt. Generally, we realize these type of interrupts, maybe this is one example where we are realizing them as a timer counter. Where we can see this part code, this is for the timer count. So this is a countdown timer. If count not is equal to 0, then you are basically decreasing the count. And this is your main execution part, where you have set some initial value of this timer count, and while this is not equal to 0, you are executing your normal code. So if this is the main idea, how you are realizing your interrupt and your main code, and how your interrupt is affecting your main code, then we can model this scenario with these state or state transitions. You can see this is the state for interrupt, when either it is disabled or it is enabled. So initial state may be idle. From there, you are asserting some value, and from there, still this timer count is not equal to 0. from there, yes, not equal to 0, then it is jumping to enable state, and from here it is step by step it is decreasing the count and it is coming back to again to the idle state. And once in the idle state, whenever your main program again setting some value, asserting some value, some initial value, then this timer is going again, starting its down count and coming to 0. So this is the same concept where you have actually divided this two states of your interrupt, one in active state and the active state. In your active state, you can see if your timer counter is not equal to 0, you are down counting. In your inactive state, what you are doing, you are basically executing. While timer counter is not equal to 0, you are actually executing, continuing your execution. So this is how, with this inactive and active states, you can model your interrupts and you can map your interrupt with your existing main program. One concept I want to share with you, that maybe sometimes in your, whenever you have done that microprocessor, microcontroller programming, sometimes you have already used this watchdog timer. This watchdog timer, when we generally use in our general purpose programming, we use them, yes, as interrupt. But this is not the purpose of watchdog timer. This watchdog timer is this concept of interrupting. Like you are interrupting your main program and you are requesting your system to service something else. That was used to save or to add as a safety feature to your embedded design. In some specific cases, where this type of embedded systems, embedded softwares, you are designing and you are placing in some distant place where you do not have physical access directly to control those cyber physical systems or embedded systems. So spacecraft is that type of example. So you have seen that sometimes we need to do some system reset, and some problem gets solved with the system restart and system reset. But the problem is, if one second, how do we recording this? We have started. Oh yeah, recording. So in that case, if your embedded system or the software in execution, if it is placed in some distant place, you do not have the access to restart that system if required. So watchdog timer was mainly proposed or mainly developed to serve this purpose, but using the way an interrupt works. So it was first proposed, this type of requirement of this type of timer or this type of watchdog was first failed when there is a failure in this Clementine spacecraft in 1994. At that time, there was a computer failure, that is embedded software failure, and it was required that we need to restart make a restart in that spacecraft. But that soft reset or hard reset was not possible, or some technique was not integrated with that spacecraft to perform that reset. At that time, it was failed that we should add, and we need to have some mechanism so that we can perform distant reset. And that is why this watchdog timer is mainly important. So what is the idea here? The idea is exactly same how we work in case of interrupt. This is watchdog timer is another like a similar timer, down count timer. So this watchdog timer, it is counting maybe starting from a start count to 0. What it is expecting, you can see, it is expecting one input that will restart this watchdog timer. Like this is your main system and this is your watchdog timer. So this watchdog timer will give some input, maybe starting value that 2000 that will set within the time just before this watchdog timer is reaching to the value 0. The count is reaching to the value. So the time there should be a time delay, and it is expected within that delay, or we should say within that delay interval, this watchdog timer is expecting one input, restart input from this computer. If it is given, it is fine. It is working properly. That is the only service this watchdog timer is expecting. If it is not getting that input, this watchdog timer will send one input to this your main system so that it will get a periodic restart. Not periodic restart, sorry, it will get a restart. That means watchdog timer is like a monitoring device. So far, it is getting or it is receiving some restart input within a particular interval. It is considering that everything is going fine in your main system, main embedded component, main embedded software. But if that delay is not, reset or restart input is not coming from your main system, main embedded software part, then watchdog considers that maybe due to some reason this main embedded software, main system got hung. There may be some possibility of deadlock, or there is maybe some reason due to which that the normal execution of your software is not proceeding. So that's why it will send a reset signal so that it is considering it will reset from the start, and everything again with this reset execution, everything will fall into place. So this is a monitoring purpose for that is the main purpose of watchdog timer for which it was developed. And nowadays when we are using normal microcontrollers or microprocessors and we are doing some programming or something like that, sometimes we use that watchdog timer as an interrupt provider. You can understand, right? This is also a timer. So basically whenever we are thinking about an interrupt, we can think of a timer. So for that, of course, we can use that as a normal interrupt provider, normal timer. But basically, when we are considering watchdog, that circuit was developed for monitoring your embedded software that is distantly placed. Okay, so this is just one extension, or this is a concept related to interrupt. That's why I thought to mention it. So the main thing what we have considered, that after my pipeline strategy, after my memory organization, the third thing that may affect that is going to affect my embedded software computation time, overall processing time. The third point is we should know how we are handling interrupts, or we may predict, maybe some prediction analysis can be done, that how frequently I can expect some interrupt, and that way I can actually estimate if whether whatever task I have, whether I can meet the real deadline requirement or not. Okay, so this is the basic concept of interrupt and how it is actually, why it is actually affecting the embedded software execution. Next, we will take one simple example and we will see how we are writing that and what more added points when we are actually writing in terms of a programmer, in terms of a software developer, what more added features we should consider and we should take into account for our proper processing or proper execution of our embedded software. So this is one example. This is straightforward. I have taken this again from that group Leeds Asia, so you can go there. But you will find those who are not from CS background, or those are not. Maybe most of you have done the programming and data structure initial courses. But for this operating system concept, if required, only the terms are given in this the section, the Leeds Asia book. So if you feel that there is some problem in understanding, just refer to that Galvin group or Galvin slides. That for memory part I have already shared. Maybe for deadlock also I will share. So only those terms is given in the book in the anticipation that you have already those background. Okay, so if you have those who are not having that background, just please refer to the Galvin book in background. So this is one example we will start with. This is a basic observer based program. Observer is observing some pattern, or in a straightforward way, it is listening or observing how a value is getting changed and taking one action based on that. For example, if you remember, we have started our discussion with that parking lot counter example. Remember, where we have talked about whenever you are having incoming car or outgoing cars coming into or going out from your parking lot, their respective sensors, in sensors or out sensors, they are basically taking the count, and effectively internally there is some processor, maybe some counting devices counting how many cars are there at present in the lot, or how many vacant places are there, and that count is getting displayed in our display, in one display. So here, if you think about this observer pattern, what you can map to this problem, this observer may be your display board or the display unit. That is mainly observing how the total count is getting changing. So that input is coming from your input sensor or output sensor. So if you actually follow different kinds of this CPS examples, you can map this a very common scenario. That's why they have taken this example. So there will be two things. There will be some update function that is updating the required value X. Okay. And there will be some observer that we have termed as listener. The listener is observing or listening how this value is getting changed and taking some action. Here, that action we have mentioned as this printing functionality. That is how the value of X is getting updated. That updated value is getting printed by this listener. That means there are two functions when. That is this, you are adding maybe one observer or multiple observers you are adding, and they are observing the change and they are printing. Okay. So this is the program written. You can go step by step. I will just tell two main blocks. One is, this is the update function. Okay. When there is some new X, there is some change of X, that is getting notified. And this X is, of course, you can understand that is a shared, globally shared variable. And this is observers. Now these observers or listeners, maybe this is one single one, or maybe randomly increasing. In case of that, for random increase, they have considered some dynamic allocation of memory. Okay. So those add listeners will actually call this function print, is mapped with this function print, and they will take the value, updated value of this X, and they will print. Now there are two concepts. One concept is still very straightforward, when you need to do this type of dynamic allocation of memory. How we will do that is based on linked list. Where linked list means the basic concept is wherever you need to allocate some new memory, you are basically allocating a node in the list and one link that is pointing to the next node. Or maybe if it is your starting node, from starting node to you are again allocating one new location, new memory location, and you are linking your head node maybe to this new node. If there is no link, that is the end part is given as null address. So this way, whenever dynamic allocation takes place, if you are considering linked list, this link is actually two things: allocating some memory and linking the memory to the previous list. So that is used and that is shown how you are adding listeners, and this linked list concept is used here. The second thing is that these are separate functions you are writing, and these functions you are calling as and when required. Okay, and you are basically mapping, you are pointing from one function to the other. So when you are actually writing a single function or this function calls, multiple function calls, this is maintained by stack. Now only this stack, this what it is written, those who know how the stack works and how this function call is getting handled, it's good. But I will explain a bit because this is very important in few cases, especially when we are talking about embedded computation or embedded software. Because when we consider this embedded domain, we consider a few limitations. We have to keep in mind that everything is very restricted. Our deadline is restricted. So I have to, whenever I have this real-time requirement, I have to finish my task within a certain deadline. Number one. Number two, my memory is restricted. It is not that as and when I required, I can extend my memory. Okay. So my RAM, everything is very much restricted. So within that restriction, what are the typical features I have to keep in mind that should go as per with my embedded requirements? So this is a simple program execution. I hope some of you already know that when I have like this, three functions A, B, C, you can see here also we were dealing with multiple functions and we are calling one from the other. So same example it is given A, B, C, and from within A we are actually calling B and C. B, this is B, this is C, and this is the main function where we are starting the execution. Starting first calling A. That means whenever I am one of my functions in execution, or whenever I'm I'm calling a new function in my main memory, in main, that actually that call or that execution writing of instructions actually reflects how my program related stack, where I actually store all related informations of my program, actually what that is getting changed. So initially, if you see, this is if it is my program stack, initially I have loaded the frame related for my main memory, my main program. When my main is calling this A, function A, from main to A, this is a call that is reflected in the stack, and a frame for this function A is getting stored. What do we mean by frame? Frame means, okay, you can see in this. Frame means associated local variables, associated registers, and some other arguments. Everything getting stored. And one most important feature, that is when you are calling from one function, maybe from main to A or A to B, then this is the return address. Like when you are calling A, again you go to back here, within A, first you will execute B and then you will come to C. So when once you are calling A to B, then again A to B both are getting stored. But when you will complete the execution, you will be returning from B to again A, right? Then you will do the execution of C, and then again so on. It will proceed. Interesting, important part is that since you have to return from A to whenever you are calling A to B, you have to, after the completion of B, again you have to return from B to A. So that return address should be stored within this frame for A. So this is how basic program stack is maintained when we do our execution. Whatever internal variables, the local variables we deal with, those get stored in this stack, and we fetch them one by one as when required in this fashion. Okay. So now you have already understood that this when I'm calling a function Q from P. So P is my calling function and Q is my executing function. So what I have to store, what are the parameters I have to store, so that when I'm moving my pointer from one function A to function B or P to Q, and again I have to come back from B to A, how can I come back? I can again fetch this return address from the stack, and exactly that I will load to my program counter, and I will come back there. So this is, we perform our, in spite of the fact as a software developer, I'm just writing these instructions, A after B, then execute this function, that, and all, just in the form of instruction. Actually at the back end, related variables are getting stored in this way. Okay. So for straightforward programming, this is fine. But the challenge comes when we go for some recursive programs. What does it mean? Recursion means when within a program, I'm again calling the same program, but for different parameters. That means whenever you are computing some factorial for this n, and you are actually coding in this way, this is the recursive way of coding. That time, recursion we generally apply, we generally follow, because it is very straightforward way to code. When we can actually develop some recursive relation in our request specification, then if we are tempted to go to that recursion direction. But the problem here is, if we go for embedded scenario, if we go in this direction, now you know that your program stack, that is limited. Now when you are actually in this initial fact n, then you are calling this fact n minus 1, then again you have to grow your stack, and since it is a recursive program, you have to go till the end, and then only you can compute, and you can traverse down again this way to compute the whole thing. So for the whole computation, you have to store in your stack this intermediate function parameters or function values, function entries. Now this is not very desirable, or this is not, sometimes this can be catastrophic, as you understand that the size of the stack, that is deterministic, and that you have already maintained, or you have already decided initially. Second thing, we in general, when we talk about this embedded domain, we generally work in very restricted amount of memory requirement. So in that case, we may, or for a very huge value of n, we may or may not support such type of huge stack requirement. Things become worse when we take this type of example. See, this is for Fibonacci computation. Now in this Fibonacci computation, again, in this the requirement is that I have to compute, if I am going for the recursion direction, I have to compute this fib I minus 1 and also fib I minus 2. So here you can see you have to store more inputs, I mean more intermediate details in your program stack. On the contrary, if you, for these type of problems, if you follow this type of for loop type of handling, that is, you are avoiding, maybe your code is getting expanded, your initial code is getting bigger, initial code getting a bit complex, but still you are avoiding this recursion and you are handling them in the form of a loop. In this case, the advantage is that maybe your code is, sorry, 1 second. Your code is not as smooth, as smaller as the recursive version, but at least you can ensure that these types of problems like stack exhaustion, that may not happen. You will not face that type of problems. So that way it is better if you do not know the limit. It is not always. Sometimes of course you can use recursion, but if you do not know the limit, so in some cases it is better to avoid these type of recursion problems to better stack handling, stack management, or memory management. Okay. So next we will talk about thread. Okay. Before that, is there any question?
Ma'am, other than the stack handling, there is like
Yeah. Yes.
sometimes the recursive solution can also be the optimum solution, but still it would be better if we implement using a loop because it would not cause stack handling problems. Ma'am, is that right?
Yes.
Uh, so, but even though both the solutions could be optimum, ma'am, for example, in the
Yes.
Fibonacci,
Both the solutions are correct.
yes,
Okay.
ma'am.
Both the solutions are correct. Both. I mean, that's why we can go in. That is, both the options are correct. Nothing wrong with any of them. As a software developer point of view, when you are coding, both the ways you will code, you will get the correct result. But the problem is when you are going to execute based on your whatever constraints you are working on in the embedded scenario, there may lead to some problem.
Yes, ma'am.
Okay. Any other question? No, right? Okay. Next, we'll talk about, since we are talking about multitasking scenario, concurrency and multitasking, and what are the different challenges we can face there. So one important discussion should be about thread. We have already mentioned about thread earlier, that whenever you we use thread, of course, we need to have some support from the backend. This is first thing. Second thing, nowadays there are different compilers. Whenever we are programming and we want to implement thread, based on that support, these compilers give us a front-end support, instruction level support to create and the thread, terminate thread, and how we can process with the thread. So this is the basic idea about it. But before that, we should understand what are the different sharing strategy a thread takes, because that will actually affect later on when we will discuss about mutex and other things. So when we are talking about thread, we can see this is my one process and this is my other process, and both can have multiple threads. What do we mean by threads? Threads are lightweight processes. Now, why do we call it lightweight? Lightweight means whatever processes have, threads is having almost the same thing, but some things are not required, some things are missing. That's why whenever we are creating a thread, some less parameters are required. And thread is a huge support when we are actually trying to go for multitasking or concurrent scenario. Now, when you will be creating any process, there will be huge, there are different parameters other than the stack, register, program counter. There are CPU management, memory related information. Everything should come into picture for a process. But threads are simpler. They just deal with some stacks, registers, and pieces. Now, the basic concept is this is for single threaded scenario, single tasking. This is for multitasking scenario when we are having multiple threads in a processor. Now we can see for this thread, some components, those are very specific to that thread, like this registers, stack. This is very specific to this thread. I mean each and every thread. But thread is sharing multiple threads. They are sharing data, some add files, file storages, code, those things. Some parts may be dedicated to thread, some parts are shared. So that way, whenever we are going for a thread level implementation, it is straightforward that we will get some supports from our library, front-end library. That will see, this is a library given constructs that will help us. We can create a thread with some thread ID, and we can map it with some program or something that on the code what the code thread will actually do. Then this is from pthread join that will basically take care of that whether the thread has been terminated properly or not before you are going to the next level of instruction. So everything these supports I will get from my compiler. So that is very straightforward and given. But what I have to think in my algorithm, or when I'm actually going for this multitasking scenario, especially with some shared resources, there we have to consider that how when we two threads are going to work upon some shared resource, what will be the strategy? So one strategy is mutex based locking. So you can think that mutex means you can think maybe one you can say one variable. Maybe this lock is a variable. You are setting it one, and that is also another shared variable. Now, whenever any thread is entering in a situation where it is starting to access a shared variable, it will set the lock high, or it will set the lock 1, and it will continue execution with this shared resource. Now, whenever the execution ends, it will come out and it will unlock that particular shared resource. Okay. So based on this, if there is a second thread 2, it will check that, and it is interested to work on this shared resource. Of course, it will first check the log value. If this log value is, it will say check if it is already set. That means some other thread is already using that particular shared resource. It has already taken the hold of that particular shared resource. So that the strategy is to wait at that time, and then once the execution of the previous thread already done, it will release that mutex. It will release that shared. It will unlock that mutex. It will release that shared resource, and the next thread, maybe thread 2, can get hold on it. So this is the basic concept of using mutex when we are having some shared resources. There are some other handling strategies also, semaphore and all. But basically, you have to understand that underlying it is something this is related to locking and unlocking strategy. When something is set locked, that means all other threads cannot do any modification on this shared resources. Sometimes reading is fine. If multiple threads are trying to read, reading is fine. But when there is some requirement on write modification, that time these type of mutex or mutual exclusion based strategies, they are very helpful. They are very important, not helpful, I should say. They are very important. They are obvious requirement for proper execution. Okay. So just this is fine. This is from our operating system concept. But here I will give one example that will show you that in spite of the fact you have done this multitasking, in the multitasking scenario, you have taken this concept of locking and unlocking, maybe with some mutex or other strategies, existing strategies, but you have actually incorporated in your algorithm the concept that this is two tasks. Yes. Any question? Someone unmuted. Okay. When we are thinking of applying this mutex or this locking strategy on some shared resources, we have to be more careful. We have to be extra careful. Now, this example, this is from this the one incident from Mars Pathfinder mission that is taken on 1997. That shows that how important to handle this type of locking scenario carefully. See, this is an example of Mars Finder spacecraft. Sorry. And you can see how the different tasks are scheduled here. This is a multitasking scenario in a real-time operating system. Of course, you will learn more about the scheduling techniques, strategies after this. But just you have the idea. I'm giving you the idea that when you have multiple tasks and you have real-time requirements for different tasks, that every task are having some deadline. Then you set some priority. Some tasks are with high priority, some tasks are with low priority. That means some tasks you have to finish it within maybe. Oh, of course, there are different algorithms how you will be choosing that priority, how you will be deciding this priority. You will learn after this after few classes. But high priority means whenever this high priority task is coming into picture, coming in your operating system, the resource should be given to this high priority task, and low priority task, this is given by TL and this is given by TH, should wait for this high priority task to complete first. So that is the concept of preemption. What we say, preemption means whenever high priority task is coming into picture, it is stopping this low priority task, and then it is completing the execution, and then the low priority task will continue and finish. Now the thing gets changed, or according to the law of this mutex or mutual exclusion, according to the requirement of that, this preemption can only happen if your low priority task is not in mutually excluded state, that is if it is already locked one shared resources. At that time, what will happen? At that time, this low priority task should finish its this time, the way it is holding the requirement of its shared resources. Then only this high priority task can preempt, and then again it can take hold the resources and then this low priority task again continue the execution. Okay. That means whenever there is a sharing of resources, the high priority task should remain blocked. Okay. But if there is no dependency in terms of shared resources between this high priority and this low priority task, then of course this high priority task can preempt and can enter, like in this case. Okay. Only in one case the preemption will not occur if these two tasks, they are sharing some common resource. Here it is given as R1. Okay. Now, problem that was given, that was incorporated, these type of concept has been handled in the spacecraft. There was no problem. But what was not handled, due to this mutual exclusion policy, what happened, there was, due to some unexpected error, some medium priority task got spawned. It was generated. And these tasks, since they were not any dependency with these low priority tasks like TM and TL, they were not sharing any resources. So what this medium priority task they do, they just preempted this low priority task, complete the execution, then again the low priority task started. That way, multiple medium priority tasks got spawned, got generated, and that way this high priority task remain in the hold state for a very long time, and that way that missed the deadline. And that is a very critical deadline that had been missed, and that is some kind of failure considered in this Mars-bound Pathfinder mission. Okay. So these things generated as a basically flaw in the design. Initially that was not attacked. But later on, these concept has been used many times. That we have another elective here. I cannot discuss more. That there we discuss that these type of scenarios, these type of design flaws, actually exploited many times later on by different attackers to attack different type of your design embedded softwares. So that's why it is very important to take care of these type of mutex scenarios, especially in the multitasking situation, because any labs in whatever algorithm we are designing, whatever policy we are making, that may lead to some error, and in turn that may lead to some attack against your embedded software. So when this problem initially was detected, that will lead to the failure to this spacecraft, but later on that was handled by a simple solution. There are different many solutions. Actually, this solution is also having some problem against attack, but I'm just telling the simple solution. This is solution to, okay, why now this incident we termed as priority inversion. Okay, priority inversion means, see, according to your priority, set priority according to your priority logic, in that your real-time system, this high priority task should get high priority to complete its deadline. But the situation that happened, that led to a scenario where your high priority task actually waited for very long only, and only by some medium priority task. So priority is inverted, and here the medium priority task got the actually execution execution priority. Okay, so it got executed, a medium priority task executed before some high priority task. That's why this scenario is called priority inversion. Now what is the simple solution given to avoid this? To avoid this later on it was considered whenever any mutex, any task is owning any mutex, which is setting any mutex as locked, immediately the priority of that task is raised to the typical possible high priority. That means now in the priority inheritance solution, in this solution, your lower priority task TL will be given the priority of the higher priority task. So now the whenever TL is actually locking any shared resource, getting hold of any shared resource, it is achieving the highest priority so that no intermediate task can actually interrupt it, whether or not it is having any dependency on that, resource related dependency on that. And then once it finishes release the shared resource, after that the next priority, next task with the next priority can get hold of your operating system or get hold of the resources. So this is the idea. This is the example shows how this mutex handling or shared resource handling can be very much critical, and that can lead to your deadline miss, which is very critical requirement. I mean, meeting your deadline is the most critical requirement when you are actually designing any embedded software or real-time software. So this part should be taken care of, that in spite of the fact we are applying this mutex concept, in spite of the fact we are adding some locking or unlocking features on the shared resources, how the whole policy we are making in terms of our other tasks and in terms of our task priorities. Okay, so is there any question on this? Any question? Is it clear? Hello? Are you there?
Yes, ma'am.
So any doubt as of now?
No, ma'am. But we'll go through it again, ma'am. Then we'll ask in the
Yeah, you just go through it and just I will ask you again maybe, whatever you understand, because this is one of the most important requirement why we should deal with mutex carefully in embedded scenario. Okay, so that's all for today. Just go through it. Obviously, go through it once, and whatever doubts you have, just ask me. Okay. So that's all for today. If you are not having any question, we can wrap up here. Go through it and then let me know whatever questions you have. Okay, thank you. Thank you. We can leave the link, I think.